Hi, this is lecture 16 of Engineering Physics 1. In this lecture, we will move away from conservation laws for a little bit, and we will start a new subject. The subject is rotations. We will be talking about rotations and things that are related to rotational motion for the next 2 weeks. You can find slides that accompany this video recording on Canvas. So, what are rotations? For when we were thinking about motion before, we were thinking about an object that moves in space. This is one possible motion called translational motion, but there are other types of motions that a rigid body can sustain, and one type of motion is a rotation. Rotation is very familiar to us from everyday life. Bicycle wheels rotate around their axis. Car wheels rotate. If you take any rigid body, for example, a book or a pier, you can choose an axis of rotation, and you can rotate that object around that axis of rotation. Since rigid bodies like to preserve their shape, once you fix the axis of rotation, there are basically only two kinds of rotational motions that this object would participate in. One is rotating around this axis in a counterclockwise direction, and another thing that this object could do is rotate in the clockwise direction. So once the axis of rotation is fixed, you can only rotate in one of these two directions. We will start by kinematics. Kinematics mathematically describes how rotations work. So the beginning of this will be, kind of heavy with algebra, but good thing is that lots of equations that we will have to use will be familiar to you from first few weeks when we were studying kinematics of translational motion. On slide number 2, you can see how different concepts are related between translational motion and rotational motion. So, for example, for the translational motion, you have this notion of displacement. So when something is moving, we can describe where that thing is with a displacement vector, or we can describe it alternatively by functions x as a function of t, y as a function of t, z as a function of t. And for rotational motion, you don't have a displacement because things stay in place. What we do to describe this rotational motion is the angle. So angle is now kind of like a displacement. So you will look at this wheel, and if this wheel rotates, then to describe mathematically with numbers by how much it rotated, what you will do is you will measure this angle, and then to describe this rotation, all you need to know is you need to know how your angle, let's call this angle theta, depends on time. If you know how angle depends on time, then you basically know everything about rotation. For translational motion, we had velocity, and velocity was a derivative of displacement, a time derivative. It told you how fast displacement was changing. And for the rotations, you have angular velocity, which is similarly time derivative of your angle. For translational motion, you had acceleration. Acceleration was derivative of velocity, and acceleration was telling you how fast the velocity was changing. For the angular motion, for the rotation, you will have angular acceleration. Angular acceleration is derivative of angular velocity, and it tells you how fast the velocity is changing. For the translational motion, we had a notion of mass. And the meaning of mass was that if things had high mass, then they were difficult to get moving. Similarly, for a rotational motion, we will have something called the moment of inertia. It's usually denoted by letter I. And rotational inertia will tell us how difficult it is to get things rotating, spinning. Instead of energy, regular energy, we will have rotational energy. And instead of forces, we will have torques. Let's start with the angles. Angles are easy to measure. If you have a circle, then you can measure the angle in degrees or in radians. One full rotation is 360 degrees. And radians are kind of less familiar, but in mathematics, very often more convenient. Radian is an angle, just to remind you, I'm sure you know it from your math classes. Radian is an angle for which the length of this arc is equal to the radius. And we like to use radians because we will later see that when you write down, there are some, quite a few equations that when you write them in radians, they look simpler compared to degrees. So 1 radian is roughly 57 degrees, approximately 57 degrees. And this whole rotation, one whole rotation is about, is exactly actually 2 times pi radians. You can use this definition to translate between radians and degrees. So it's approximately 57 degrees, but if you need a more exact number, then 1 radian is 360 divided by 2 pi degrees. The standard convention is that if something is rotating counterclockwise, like so, then this rotation is positive. So if I have this spike here, and if this spike moves 20 degrees counterclockwise, I will say that the change in the angle is positive 20 degrees. And if things move clockwise, for example, if this spike moves clockwise by 20 degrees, I will say that the angle changed by negative 10 degrees. So just to remind you, you have your angle that changes in time, then angular velocity is, angular velocity is derivative of your angle with respect to time, and angular acceleration is derivative of your angular velocity with respect to time. If your rotation is simple, by simple we mean acceleration is constant, then you get simple equations. When you have a constant acceleration, then your angular velocity is your initial velocity plus acceleration times time. And your angle is whatever your initial angle was plus initial velocity times time plus angular acceleration times time squared divided by 2. If you look at these equations, they will look very familiar, and that's because they are one-to-one copies of the equations that we had for translational motion. Just to remind you, for a translational motion, if you had constant acceleration, then your position was your initial position plus initial velocity times time plus acceleration t squared over 2. and your velocity was changing as initial velocity plus acceleration times time. So basically, the only thing you have to do is you have to replace linear terms by corresponding angular terms, and all the rest of kinematics simply works. There is one subtle difference between angular motion and translational motion that we have to always keep in mind. With the translational motion, as you move, you always, if you move in one direction, you will always get further away from your initial point. But with the rotations, if you are rotating, even if you are always rotating in the same direction, you will be getting back to your original position. That's because rotations are periodic. Once you move by 360 degrees or 2 pi radians, you get back to your original position. So that's kind of an important thing to keep in mind when we have to deal with the rotations. Before moving further, what I want to do is I want to look at 2 problems from your textbook. These problems are about rotational motion, about kinematics. Let me start with problem 16.1, which is number 3 in your textbook. This is on slide number 4. So in this problem, what you have to do is you have a buttered toast on a table. So this is a table and there is a toast. And this toast has a buttered side on top. Then what happens is that by accident, this toast falls. And as it falls, it starts rotating. There is Murphy's law. And as it's rotating, in the end, there are 2 possibilities. One possibility is that it will end up buttered side down, and the second possibility is that it will end up buttered side up. And that kind of depends on how many rotations the buttered toast will do before it falls. They tell you that the distance from the floor is 76 centimeters. So this distance is 0.76 meters. And they ask you, what are the angular speeds that will make your toast hit and then topple to be butter side down? So what's happening here is that you're making one rotation. So your the buttered toast was originally like this. Then it will rotate. It will rotate as it falls. And if it ends up like this, at 90 degrees, but just slightly tipped to the right, then when it hits the floor, it will probably fall the butter side down. And if it if it's rotating slower, then it will hit the floor kind of like this, and then it's very likely to fall down to the left and hit the floor, the bread side down. Now, if it rotates even faster, then at some point it will rotate so much that it will look like this. Again, almost 90 degrees, but slightly tipped. So when it falls down, it will fall down the butter side down. And so in this case, it falls bread side down, and in these 2 cases, it falls the buttered side down. So we're interested in the range of rotational speeds that will put me in this situation, between this limiting case and that limiting case. To solve this problem, what I will do is I will first I will compute how long exactly does it take me to fall from the edge of the table to the floor. To do that, I can ignore rotations. I have something that's falling, and it doesn't really matter whether it rotates or not in this case. And if you go back to the first week's material, or first 2-3 weeks material, you will probably remember that when something falls, the distance that it travels, h, is equal to gt squared over 2. In this case, my h is 0.76. Let me take g equal to 10 for simplicity. So 10 divided by 2 is 5 t squared. From here, my t squared is 0.76 divided by 5. And my t is the square root of 0.76 divided by 5. Let me quickly crunch these numbers and get back to you. Okay, so this is 0.4 seconds. Now I know that it takes my toast 0.4 seconds to hit the floor. Now let me think about what I want my bread to do in those 0.4 seconds when it comes to rotations. So when it comes to rotations, if I want my bread to fall the butter side down, then in those 0.4 seconds, I want it to, starting from this position, end up either in this position or in this position. Anything in between will look like so, or like so, and will give me result in butter side being down, which is what I'm looking for. Now let's think about by how many degrees does my bread have to rotate to get from here to here. If you look at this, there is no kind of method for doing this. You just have to just look and apply your comments, your geometric intuition to get this. If you look at this, you will see that this is 190 degrees. So from here, if this is 0 degrees, then this will be 90 degrees, this will be 180 degrees, this will be 270 degrees. Let me also draw the butter so that it's clearer. So from here to here, oh, actually, sorry, I take it back. From here to here, it's 90 degrees. From here to here, to get from here to here, I need to rotate my bread by 90 degrees. Okay. So my bread has to rotate by at least 90 degrees, but anything between 90 degrees and this position, which is this here, which is 270 degrees, is fine. So everything between 90 degrees and 270 degrees is fine. If it's less than 90 degrees or more than 270 degrees, then it will end up bread side down. So in 0.4 seconds, I want it to rotate by an angle that's between 90 degrees and 270 degrees. This means that my velocity, my angular velocity, should be between 90 over 0.4 degrees per second and 270 divided by 0.4 degrees per second, in between these two numbers. So 90 divided by 0.4 is 225 degrees per second, and 270 divided by 0.4 is 675 degrees per second. I'm not gonna translate this into radians. You can do it, but this is basically the range of spinning velocities that will result in my toast falling down, butter side down. And if you don't get this from the video lectures, you know that I'm running Zoom help room every Monday, Wednesday, and Friday. So feel free to join and ask me any questions that you may have. I will now move to problem 16.2. This is on slide number 5. And in this problem, what I have is, I have an engine. And this engine is rotating, but it's speeding up. So in the beginning, it had an angular speed of 1200 revolutions per second. Sorry, revolutions per minute. And then it accelerated, and towards the end, it had 3000 revolutions per minute. All of this happened in 12 seconds. There are two questions. The first question is, what's the angular acceleration in revolutions per minute squared? So let's do that first. What's the acceleration? Acceleration is change in velocity over change in time. Change in velocity is from 3000 to 12,000, which is 800 revolutions per minute. And change in time is 12 seconds. I have to convert 12 seconds to minutes. 12 seconds is 1/5 of a minute. So that's 0.2 minutes. So this was easy. 800 divided by 0.2, that's 4,000. So turns out to go from 1200 to 1300 in 12 seconds, I have to have an acceleration of 4,000 revolutions per minute squared. And the meaning of this is that if I waited for 1 minute, then my speed would go up by 4,000 revolutions. Now let's look at part B. In part B, the question is, how many revolutions does the engine make during this 12-second interval? So how many revolutions? For that, I will use the formula for the angle. The angle is my initial angle plus my initial velocity times time plus my acceleration times time squared divided by 2. So if I move this angle over here, I will get change in my angle is equal to initial velocity times time plus angular acceleration times time squared divided by 2. So they ask me how many revolutions. I don't have to rearrange this equation. I can just use my numbers. My initial velocity is 1200 times 12 seconds plus 4,000 times 12 seconds squared divided by 2. And since my velocity and my acceleration are in revolutions per minute, I think it's better if I rewrite my seconds in minutes. So instead of 12 seconds, I will write 1/5 of a minute. So 1/5 is 0.2. And here I will write 0.2 squared. Okay, the rest is simple. I will have 240 here plus 2000 times 0.04. And this is 240 plus 80, that's 320 revolutions. So as my car engine goes from this to that in 12 seconds, it makes 320 revolutions.